Okay, welcome to Chapter 9. We are going to actually be dividing this into two different sections. So we're going to do sections 9.1 through 9.3, and we'll do 9.5 through 9.7 after the break. So we're going to start off with a lesson on sequences and series. Now, what you should learn is how to use the sequence notation to write the terms of a sequence, and of course we're going to define what a sequence is for you. You're going to learn how to use the factorial notation. You might have seen this on the ACT. That's that special number with an exclamation point beside it. And we're going to use summation notation to write sums and then find the sums of infinite series. So let's first begin by talking about what a sequence is. A sequence is a function, an infinite sequence is a function whose domain is a set of positive integers. Okay, so by positive integers, we mean 1, 2, 3, 4, 5. Okay, essentially whole numbers. Okay, not including 0. So the function values are the terms of the sequence. Okay, so if the domain of the function is finite, meaning it has an end, then our sequence is going to be finite. In fact, however many numbers of terms are in your domain, that's how many numbers are going to be in your sequence as well. So when we talk about terms of a sequence, and we try to have a notation for that, we use the sub notation. So a sub 1, a sub 2, a sub 3, a sub however many out to a sub n and beyond, right? Okay. One thing I want to make sure you know, though, is just because our domain is positive does not mean that all the terms will be positive. We can have negative terms, okay? So let's do an example here. We're going to write out the first 4 terms of the sequence, and the sequence is going to be defined by a sub n, so a sub however many terms you have, okay? So we want a sub 1, that means we're just going to have 4 times 1 plus 2 times 1 squared. Well, 1 squared is 1 times 2 is 2. So 4 plus 2 is 6. So a sub 1 is 6. A sub 2 is going to be 4 times 2 plus 2 times 2 squared. Well, that's going to be 2 squared is 4 times 2 again is 8. So 4 times 2 is 8. So a sub 2 should equal 16. Okay. A sub 3, well, that will equal 4 times 3 plus 2 times 3 squared. 3 squared is 9 times 2 is 18, and 12 plus 18 is, of course, 30. So a sub 3 is 30. A sub 4, that's going to be 4 times 4 plus 2 times 4 squared. 4 squared is 16 times 2 is 32. So 16 plus 32 is going to be 48. So a sub 4 is 48. So looking at this, the first 4 terms of our sequence are 6, 16, 30, and 48. Okay? And my sequence keeps going on, but these are the first 4 terms, right? And we have something that defines each of our terms in our sequence, kind of like a function, right? So the only thing is n only takes numbers 1, 2, 3, 4, 5, and on, okay? So we're not going to have values in our function between 6 and 16 or between 16 and 30, okay? If we were to graph this, this would just be a series of dots on a graph. So, let's talk about writing sequence rules, okay? And we call that the a sub nth term. So given a sequence, we want to be able to figure out the rule that defines that sequence, okay? So let's take a look at what this sequence says here. We have 1/3, 2/3, 1. 4/3, 5/3, and on. Well, if we look at this, 1 is really 3/3, right? So a sub n will equal n over 3, right? A sub 1 is 1 over 3. A sub 2 is 2 over 3. Okay? So there's no real science to finding A sub n. There's a few different techniques, but a lot of it is just analyzing what's going on with the function, what's repeating, what do you see happening if you input 1, 2, 3, and beyond. Okay? Now another way that we have of writing sequences is called recursive. And recursive sequences are different. We start out needing two parts. The first part is we're going to have at least one or more starting values, okay? And then we will have a rule that defines all those subsequent values, or the values that follow, based on those starting values. So an example is if a sub 0 equals 2, and I found a little typo here, this should say, this should say a sub k equals a sub k minus 1 plus 5. So equals a sub k minus 1 plus 5. A sub k. Okay, so if a sub 0 equals 2, then a sub 1 will equal a of 1 minus 1, which is a of 0, plus 5. So that will equal 2 plus 5, which is 7, right? So then we have a sub 1 equals 7. A sub 2 equals, again, and that a sub k minus 1 is our previous value, okay? So 2 minus 1 is 1, so we're going to use value of a sub 1 and add 5 to it, which is 7 plus 5, which gives me a value for a sub 2 of 12, right? So you can keep doing this, and all we're doing is we're saying, hey, we are adding 5 to the previous value here, okay? And you may have seen this before in Algebra 1 or Algebra 2. Now let's talk about factorial notation. Factorial notation is a special function, and we define a factorial as a set of numbers that starts at 1, a set of integers that starts at 1, and goes and we multiply all the numbers from 1 up until we get to this nth number, right? And we multiply all those numbers together. So the pattern is, say we've got 2 factorial, that would be 1 times 2. 3 factorial is 1 times 2 times 3. 4 factorial is 1 times 2 times 3 times 4, and so on and so forth, right? There's only a couple special ones. 1 factorial is obviously going to be 1, but 0 factorial is also 1, and we define it that way, okay? So if you had 14 factorial, you'd multiply the numbers, the integers, 1 through 14 together, okay? And so that's why we have a factorial button on scientific calculators, because this can get to be a really cumbersome type of thing to have to do. So we have a factorial button that calculates that out for us. But that's what a factorial is. So we will use this in a lot of our different functions, especially to do with permutations and combinations that we'll cover in the second half of Chapter 9. So let's do a little bit of math with factorials, because factorials have this property of multiplying all these different numbers together, and sometimes you can actually have some pretty interesting math that goes on with it. So let's look at the problem 2 times n factorial. Well, because this is all multiplication, we're taking n factorial, which is a series of things being multiplied together, and then multiplying them all by 2. We can actually apply the associative property to it, because it's all multiplication, so we can use the associative property and figure out what n factorial is first before we multiply it by 2. Okay? Now, that is different from this function here, where I have 2n factorial in parentheses. Okay? What this means is we're going to go and keep multiplying numbers together up until we get to the number 2 times n. Okay? So that's a little bit of clarification on what the different notations mean. If I have 2 parentheses n factorial, then I take that to mean 2 times 1 through n multiplied together. If I have 2n factorial in parentheses, I multiply all the numbers from 1 to 2 times n together. Okay? Now, let's do a little bit more math. I want to show you how you can break apart factorials into smaller factorials. So if I'm looking at n factorial here, recognizing that's 1, 2, 3, 4, 5, 6, all the way up to n multiplied together, right? I can take one of those out, okay? So I could say that's really n times n minus 1 factorial. Or I can take a couple of them out. I can say it's n times n minus 1 times n minus 2 factorial. An example with real numbers would be to say 7 factorial is the same thing as 7 times 6 factorial, and it's also the same thing as 7 times 6 times 5 factorial. Okay? So if we recognize this principle, and we have several factorials multiplied or divided together, then we can break this up. And let's take a look at this. Recognizing that 10 factorial is 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10, right? And then 3 factorial is 1 times 2 times 3, right? And 8 factorial is 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8, right? Well, if I'm multiplying and dividing like I have shown here, all these are going to cancel out, right? So I'm really left with 9 times 10 over 1 times 2 times 3. So when I have a 10 factorial, I can cancel out things like that, okay? So that's left with 90 divided by 6, 90 divided by 6, which is 30 divided by 2, which is 15, right? Okay? So that cancels out pretty nicely, okay? And you can do a lot of different math problems with this, and if you look at some of the problems on page 645 in the text with example 6, you'll see more examples of how these can cancel out. And we'll do some more examples in class as well. Now let's take a look at summation notation. Now this chapter intro seems like it's just introducing a whole bunch of random type things, but we're going to use them all in chapter 9. And one of the other things that we need to know about is sigma notation. Now sigma notation is a shorthand way of telling us that, hey, we want to add up a bunch of different things, okay? So if I see this big capital sigma, and that's what that symbol is, it's a Greek capital sigma, that means we're going to add up however many terms we have here. So a sub I is like saying, where I is an index or a counting way, a way of counting, keeping track of things, okay? So we're going to add up all these terms a sub I. And this notation here says where I goes from 1 to n, okay? So we're going to have n terms that we add up, and they're going to go from a sub 1 plus a sub 2 plus a sub 3 all the way on out to a sub n, okay? So let's see an example of this. Here we're adding up the terms 3 plus I, and we're adding them from I equals 1 to 4. So that tells us we're going to have 4 terms, okay? We are going to have the term 3 plus 1 added to the term 3 plus 2, added to the term 3 plus 3, added to the term 3 plus 4, okay? And we can see that would be 4 plus 5 plus 6 plus 7. Adding that all up, we get 22. Yay, rah. Okay, not a big deal. The main thing that we want to get you to do is to realize how this all works. You know, this is a counting way, as a saying I'm going to have 4 times that I add up things that look like this. And wherever I have an I here, that's going to correspond with which number I'm using for my term in my counting sequence. Okay? So let's do some more practice with this. Here we have 2i minus 4 added up for the terms I equals 1 to 5. So I'll have 2 times 1 minus 4 added to 2 times 2 minus 4 added to 2 times 3 minus 4 added to 2 times 4 minus 4, added to 2 times 5 minus 4, right? So I've got 5 negative 4, so that's going to add up to negative 20. And I've got 2 plus 4 plus 6 plus 8 plus 10. So 2 plus 4 plus 6 plus 8 plus 10, right? I like to count things in groups of 10, so I'll have 10, and 8 and 2 give me another 10, and 4 and 6 give me another 10. So I have 30 minus 20 adds up to a positive 10. So the sum of all these terms is just 10. But we're doing it in such a way that it has a rule attached to it, and it has a counting mechanism attached to it as well. Let's look at this other one here, where we've got I plus 1 squared from I equals 1 to 6. So we're going to have 1 plus 1 squared added to 2 plus 1 squared added to 3 plus 1 squared added to 4 plus 1 squared added to 5 plus 1 squared added to 6 plus 1 squared. So we're saying 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared, right? So 4 plus 9 plus 16 plus 25 plus 36 plus 49, all added up, okay? And you could finish that calculation. I'm not going to spend video time doing the adding. Now let's look at some properties of sums. Okay, so these are some general rules that apply to sums. If I have the sum of a constant from 1 to n, that means I'm adding up n, however many number that n is, constants, right? So this is better seen here. I'm actually multiplying, right? So if I equals 1 to 4 of the constant 3, right? That says I'm adding 3 plus 3 plus 3 plus 3, right? So I'm adding 4 3's up, which is just the same as saying 3 times 4, right? Which is how we come about this rule that the sum of a constant from 1 to n is just that constant times the n. Okay? Here we have another sum where we're having the sum of a constant times a term a sub I. Okay? Well, if we add that up from 1 to n, that is the same thing as saying I can add up just the regular rule and then multiply it by c. And what this is just an example of our distributive property. Okay? So instead of multiplying each term by the constant and adding them all up, we're adding them all up and then multiplying them by the constant at the end. So this is just an example of the distributive property. Okay, now the last one we have is if we have terms to our summation, sum a sub I plus or minus sub b sub I. We can break that apart into two separate sums, figure that separately, and then either add or subtract based on whatever our term sign is, or the sign between our terms is, okay? So this is handy because it means you have the ability to tackle it in bits and pieces. So I can figure out this first one, figure out the second one, and then add or subtract the two as I need to based on the definition. Now we want to define what a series is. So, given an infinite sequence, a finite series is the sum of the first however many n terms of that series, okay? And then an infinite series is the sum of all the terms of the infinite sequence. And so you might have summation notation where we go from I all the way out to infinity instead of stopping at a certain number of n, okay? So we want you to be aware of this. It's not going to be too much of a big deal, but we want to introduce you to this type of definition and know that, hey, these series, okay, are when we add up a sequence, okay? So we introduce the sequence at the beginning, okay, and that has a certain rule to it. And then if we add them all up, add up all those terms, that forms a series, okay? So we have learned to use sequence notation to write the terms of a sequence. We've learned about factorials. Now you can use that on the ACT. We've learned to use summation notation to write sums. And we've learned to find the sums of infinite series.